So one way that we are able to compare the efficacy of 2D and 3D motion analysis is by considering the planes of motion that we can measure and how many we are able to simultaneously measure with the camera system that we have. Now, in the case of 2D motion analysis, let's say you have a single camera, you are therefore only going to be able to measure a single plane of motion at any one time. You could, of course, have two cameras, maybe even three, and record all three planes of motion simultaneously, which would be an improvement. But the thing to bear in mind is that the cameras aren't communicating with each other. They aren't, if you like, sharing their information that they've recorded. So the way I like to think of 3D motion analysis, we have 8 cameras, I believe, in the sports science laboratory. I like to think of that as 8 people standing around watching something happening, and the first person, being the first camera, seeing a movement occur and thinking, okay, elbow flexion, good. And then saying to the person next, did you see elbow flexion? Yes, I did. Okay, good, so did I, yes. Should we check with the third person? Okay, let's do that. And all 3 or all 4 cameras on one side conferring what the first one saw. So the information is combined to simultaneously record transverse frontal and sagittal plane motion. Whereas with 2D motion analysis, we can't do that. It's just simply impractical. So that would be our primary difference. Now, what does that mean in terms of everyday use? Well, here's an example of a quintic camera that we use in the laboratory. It's not the exact one, but it's the smaller model. And the example of this, the reason I've chosen this is because we use these cameras for 2D motion analysis, and I can pick up one of our 2D cameras, take it into any sport and exercise scenario that I want, and put it down, plug in a laptop, collect the data then and there. You can do that. You can take the 3D cameras out of the lab, but it's not easy. It's not practical, and it comes with a whole host of issues that you have to try and account for. So one way to think of this would be in terms of validity, specifically the internal and external validity of each motion capture technique, 2D, 3D. Essentially, we say that the internal validity of any research technique represents essentially its ability to measure what you want it to measure. Does it give a valid result? Is it producing a value that it should produce? For example, to give an example outside of biomechanics, are your scales giving you your correct mass? So in this sense, whilst 2D is comparable to 3D, and there have certainly been studies out there that have shown that with certain movements, 2D can produce just as high quality information, detail as 3D, the fact remains that we move in 4 dimensions, but that's something that you're not going to be able to get simultaneously with a 2D system. It's even if you wanted to, it would be challenging. It'd be easier to just use a 3D system. So the 3D cameras have greater internal validity. External validity, on the other hand, is how well you can apply the data that you've collected to the real world, to real world sporting scenarios. And by virtue of the fact that you can take the 2D cameras out into pretty much any sports scenario you want, at the drop of a hat, means that they have a greater external validity on the whole. Of course, there are exceptions. Again, I think there's even a 3D camera set that have been designed to be waterproof, to use in swimming pools and things like that, but generally speaking, 2D cameras have greater external validity, 3D cameras have greater internal validity. So, to put this in more biomechanical terms, it all comes down to the degrees of freedom and the number of degrees of freedom that each motion capture, motion analysis technique is able to record. What is a degree of freedom, I hear you cry? Excuse me. Well, again, biomechanists, we like to take complex things and simplify them in as difficult a way as possible. A degree of freedom represents the number of pieces of information that you have about an object's movement. The number of pieces of information that you have about an object's movement. So, for example, we have two graphs here, and if we just focus on the left-hand graph to begin with, we've got movement along the y and the x axis. And if we look at the sphere, which is currently sitting at 1, 1 on the xy axis, it's moved now to 3, 2. 3 doesn't matter what that is, 3 could be meters, centimeters, doesn't matter, and 2-ish on the y. Now we could break this movement down into its horizontal component there and its vertical component there. This means that the maximum number of degrees of freedom that we are able to get from measuring the movement of a single point is, or at this moment anyway, is 2. We have 2 degrees of freedom. From that we can produce a resultant movement, which is the movement that the object obviously travelled in, but that has come as a composite of its vertical and horizontal movement. So a single point moving along an xy axis has 2 degrees of freedom. If we start to consider, if that object rotates, then that's a different story, but if we assume this point isn't a sphere, it's not rotating, it's just moving along an xy axis, then we have 2 degrees of freedom. Now, the image on the right here, we have connected the dots, as it were, to create a limb segment. So the lower one here, the lower marker if you like, is currently sitting at 1, 2 on the xy axis, whereas this marker here is sitting at 2, 3. And we've connected the dots to create a segment here. Now, if, hypothetically, let's say, this segment moves, look at that, we're able to plot the movement of the point that moved. So this marker here stayed fixed, or it should have done, just about. This marker, however, moved, so we can measure its linear displacement along the xy axis, and we can additionally record its angular motion. So we now have 3 pieces of information, therefore we have 3 degrees of freedom. So let's explain this again with a single sphere. This can be a marker, it can be a ball, whatever you wish. So, this took me ages to animate, fingers crossed that it'll work. Here is our sphere. Isn't it glorious? Let's plot an x-axis. So this is our horizontal axis. This object can move, look at that, seamless, along the x-axis. So regardless of whether it moves left or right, movement along the x-axis represents 1 degree of freedom. If it moves left and then right, that's still 1 degree of freedom. That doesn't represent 2, just to avoid any confusion there. Let's introduce a second axis. We have the y-axis now. So our object can now potentially move up and down. We've now introduced a second degree of freedom. And now, bear in mind that it's very difficult to represent 3 dimensions on the 2-dimensional screen you're watching this video on. So, excuse me, this axis here, the z-axis, is meant to be pointing directly at you. It's meant to be perpendicular to the y and x-axis, but it's tricky to do. And so this is meant to represent our third axis. So this would be backwards and forwards, I suppose you could think of. And fingers crossed. Look at that. Okay, not bad. Could have been better, could have been worse. Look at that. Hours. So we have our third degree of freedom. At this point we have 3 degrees of freedom. We have 3 pieces of linear motion, up and down, left and right, backwards, forwards, movement along the x, y and z axis. But of course, this object we're saying is a white sphere. It can rotate about either or of each of these 3 axes. Therefore, this rotational motion, rotating about the y, the z or the x-axis, gives us 3 more pieces of information, which gives us a total of 6 degrees of freedom. And that is what we're able to measure with a 3D system. The 3D system can give us a full 6 degrees of freedom. A 2D system, however, is going to be limited to 3 degrees of freedom. Okay? Bonus points if you can guess, based on the image here, which 3 that would be for the 2D camera. Anyway, let's move on. So, some initial considerations before this is moving on now. Oh, whoops-a-daisy, to the more applied side. What are the first things we need to think about when setting up a 2D motion capture system? Well, as ever, and I always hammer this in to my students, the first thing you're going to need to do is collect your participant information, and don't forget to do this. So this would be your participant's age, their gender, their height, and their body mass. They're your that's your bread and butter. Not terribly specific to biomechanics, but can easily be overlooked. And it'll mean you'll just have to come into the lab again to weigh someone, which can be tedious if nothing else. You may also need to consider familiarization sessions and how many you wish to give. So let's say you're doing barefoot and shod running as a topic. If you've got a group of participants who've never run barefoot at all, ideally you want to give them a few practice goes first, just to familiarize themselves. This also gives you time to start to think about how far you need to position the camera. We'll get to that in a moment. And various other parameters. I'm getting ahead of myself a bit here. But familiarization is important if your participants are doing something that's completely new to them. You need to consider the number of trials that you want to record. As a minimum, I would suggest 3. And the concept of the Hawthorne effect. The Hawthorne effect, we're going to drift ever so slightly into psychology here now, is the notion that we're all well aware of, either consciously or subconsciously, that we change our movement patterns when we're being observed. When we're not being observed, we relax more, we move however we want. If we know someone's watching, imagine if At some point in your life, you must have been moving around, walking around, and someone you found attractive has been nearby. You might have walked more upright, or I don't know, walked with a bit more of a swagger, let's say. That is the Hawthorne effect in full effect. So moving if you're on the sort of research side of things, stepping back at the very least, certainly not, I appreciate that you all know each other and you're working together on a project, but jeering each other on or coaching, giving any advice, anything like that, it's what we need to try and avoid. We just want to record as natural a movement pattern as possible. And whilst that's inherently difficult, we want to minimise the Hawthorne effect. And that is in part done by familiarisation sessions. Or familiarisation trials, I should say. So, setting up, what do we do? What's the first few things we need to consider? Well, naturally, beforehand you will have considered what sort of movement you're going to be recording and in what plane. So you need to set your camera up accordingly. If you are using one camera or if you're using two, of course. It's important to consider why you've chosen the features that you have and being able to justify those in your report. So we have gone for this movement because we've chosen, I don't know, knee flexion because Aaron Stewart told us to, or because there's something in the literature that says it's worth looking at. The latter of those two options is the better of the two. You'll need to consider the effect that each... Actually, no, I'm getting ahead of myself. I was going to say the effect that each limb has on the other, but that's another topic. We'll come back to that in a minute. Being able to justify your results is another thing. So, or justify your movements, almost thinking ahead. So this, you choose a movement variable. Let's again say knee flexion. Okay, how is this going to be valid in, if the results go the way you want them to, what benefit is this of you measuring it? Again, is it because someone told you to, or is it because actually it's going to greatly benefit performance if we see, or reduce injury risk if we see an increased knee flexion? Something like that. So think in terms of either what effect will this have on performance, or what effect will it have on someone's risk of injury. Crucially, once you've focused the camera, adjusted the aperture, and zoomed out or in, set the zoom at least, don't move the camera once you've started. If you record one trial and then someone nudges the camera out of the way, you've got to record that trial again, because you can't just hope to reposition it in the same spot. So again, be very, very careful. A little tip, try to position your camera as far away from the movement as is possible to obviously still be able to see it, but at the same time not be too close that you're going to disrupt what's going on. This is both for the sake of the Hawthorne effect and for the sake of your data collection. Remember, you're using a camera that has a lens, and the lens will record the image, but the closer you get to the periphery of the lens, there becomes a certain distortion. We call this the fisheye effect. So you'll see this when you use the cameras. When you, if this image here, let's say, if we were viewing this through a 2D camera, then about an inch away from the border of your screen would start to become warped ever so slightly, and you just wouldn't record that information. You would want to record everything in between. So again, something to consider. Much like you see in this example here, I know this is a 3D system, but nonetheless, you want minimal clutter in the background. So if you can, as these researchers have, the lucky devils, got a completely white background. That's the dream. That's what you want. The only thing that the cameras can see are the researchers, the person moving, and other cameras. That's exactly what we want. So decluttering the image. Considering marker displacement, is the movement you're performing going to dislodge any markers? So for example here, this woman, they're performing a walking gait analysis. These markers here, these two, is there any chance of this arm brushing these markers off or nudging them aside, dislodging them in any way? If, let's say, you perform a trial and then in your second trial your participant just nudges a marker ever so slightly, you've got to start again, unfortunately. So making sure that your markers are in an area where there's a minimal chance of being shifted around. One of the most important points, and sorry, apologies, this is becoming a bit of a bullet point list, but one of the most important points to consider is making sure you know what you're doing before you come in the lab. If you have it clear in your head exactly what's going to take place, and as a team, as a group, you know exactly what you're going to be doing, then you will work all the more efficiently and you'll get things done quicker and you'll get better data. You will ideally have the markers attached to the skin. If not, you will have to wear some of our funky biomechanics lycra. The idea of this being that our markers need to be attached to you wherever possible. If not, they need to be attached to your clothing. And if, like me, I'm sitting here in a t-shirt now, if I had a marker anywhere on this shirt and I move my arm, then if the movement of the marker could represent the movement of me or the movement of the shirt. So ideally on the skin, or we get tight-fitting, get our participants to wear tight-fitting lycra clothing, but ideally on the skin. Take your time to set up the equipment, don't rush. One of the biggest issues that we see is poor focus. So when you're doing your familiarization sessions with your participant, take your time to go back and review those trials and, well, record one obviously to begin with, and just check to see if the focus is good. And if it's not, you might need to adjust the camera. You might want to record from the opposite side, depending on where the light's coming in the room. Either or can potentially affect the quality of the image that you see, because sometimes it doesn't take much to get a very blurry image, and you really need to take your time with this to make the most of your time in the lab. Anyway, I think I've waffled on enough there. Let's move on. So here we have someone performing a bodyweight squat, and look at them go. I'll give you a bit of time to really take that in. Anyway, if this person is moving in the sagittal plane, primarily, obviously there's movement in all three planes, but let's just pretend the majority of the movement, well, it is, but let's pretend all of the movement's going in the sagittal plane. And that's the plane that you wish to record in. Your camera needs to be set up so that the optical axis, that is the line of sight from the camera, is perpendicular 90 degrees to the plane of motion you want to record in. So in this case, the camera will be set up in the frontal plane, essentially, or will be recording. The optical axis will be in the frontal plane. If you were recording movement in the frontal plane, then the optical axis would be in the sagittal plane, and so on. So let's think about marker placement. Well, this is a topic that really you need to have a go with. So I won't go into any too much detail here about like how to prepare a site. You might need to shave a little patch because you can't attach markers if, like me, you're a bit of a hairy Mary, because that hair is going to move around. So that's the sort of thing you'll cover in your practical session. So let's look at some of the basics. As we know, here we have someone wearing their markers, or using this marker set here. So I meant to mention these are an example of a few different marker sets. They even have names. That's how cool we are in biomechanics. This is one of the most common, is the cast marker system here. Or this is actually part of the cast marker system. You know, I think about it, we haven't got any foot markers, but anyway, I digress. So this marker set, I'm not too sure what this is, but generally we look to apply our markers, not always, particularly if it's a cluster. So these 4 dots here represent a cluster. Here, so these are our active joint markers. Oh, these are not joint markers, these are our active markers. Whereas the markers here and here on either side of the ankle, either side of the knee, on the hip, these are our passive joint markers. So typically our markers, specifically our passive joint markers, want to be attached onto specific bony anatomical landmarks. The reason being is this thing then can be reproduced between all of your participants. Whilst we're all genetically different, we've all, hopefully, got a clavicle that we can attach the clavicle marker to here. This is really, strictly speaking, nubrium, but there we go. That's just me being difficult, but you've all got this little notch in between your two clavicle. Sorry, I mean sternal marker, not clavicle. What am I saying? Again, I need that coffee quite quickly. So this would be the upper sternal marker. Why have they called it a clavicle marker? It's not a clavicle marker at all. Poor choice of image. Moving on. Anyway, so using markers, as we say, the retroreflective markers, simplifies our analysis. It allows us to create reference points about which our movements occur. We're able to define limb segments, and we can define our axes of rotation. And all of this really allows us to get a more detailed and more valid analysis. So in the case of motion analysis, we're performing a quantitative analysis. A qualitative motion analysis, simply you just eyeballing the movement and seeing if you can determine what's going on just by viewing it with the naked eye. It comes with its own errors or issues, certainly in terms of recall, but also the human eye isn't able to resolve any movement that occurs at any speed below, anything less than 0.25 of a second. Just going to fact check that. It is 0.25 of a second. Marvellous. So it would anything less than that, so a faster movement essentially, simply not going to be able to see or get a accurate analysis. So someone taking a penalty kick in football, or performing just an instep kick in general, the angular motion of the shank, it was just, we're going to know that it's moved, but you aren't going to be able to analyse it in any detail. And of course we can give the athletes the opportunity to review their performance. This is one of the great advantages of this approach, that we can say, look, this is what you're doing and this is why it's wrong, and really boost their morale. So you will learn about the different markers locations, but here's just a few to get you started so that you're familiar with them, and you can palpate these locations on yourself if you so wish. Come on. Okay, so I've abbreviated them here, but I'll explain what each one is. So RASIS, RASIS, so this is the R stands for right and the L stands for left, and this point here is the anterior superior iliac spine. This is the most anterior superior, as the name suggests, position on the pelvis here. This is where we regularly apply pelvic markers. So there are at least two off the top of my head muscles that attach to the ASIS. This can be easily palpated by just in any position really. If you're in a seated position, you can usually find the ASIS fairly easily. The technical guide is to place your hands on the side of your hips till you find the iliac crest and work your way around to the front. The sartorius and the tensor fasciae lata have attachments on the ASIS. Once you've found it, if you place 2 fingers just below that, an inch or 2 down, and then flex your hip up and down, you should be able to feel the tendon of the rectus femoris, which originates just below that point here, around here, on the anterior inferior iliac spine. But we can't get a mark on that, so, but it helps you know that you're in roughly the right area. Here we have this point on the side of the hip, represents the left, in this case, or right, greater trochanter. Greater trochanter is fairly easily palpated again by placing your hands in your pockets, I find to be a good way, and just pushing your palms in, and either abducting the hip or rotating the hip, so standing and letting your hip rotate, so spin your foot left to right whilst your knee is extended, and you should be able to feel it moving underneath your hand somewhere. This represents the axis of rotation for hip flexion, by the way, I should also mention. The markers we have here are the the medial and lateral, that should be an M, I've just realised, femoral epicondyle. And no, that is correct, that is the correct abbreviation, I apologise. So here we have the medial femoral epicondyle and the lateral femoral epicondyle, representing the most medial lateral points on the condyles of the inferior tibia. Again, axis of rotation for knee flexion extension. And just below this, on the anterior surface here, we have the tibial tuberosity. This is the left tibial tuberosity here, which can, again, be fairly easily palpated, usually about 3, if you sit with your knee flexed at 90 degrees, about 3 or 4 inches on the anterior surface just below. Again, it's hard to visualise this without someone showing you, I know, but just so you've got a rough idea where these are. So if we place a marker on the anterior superior iliac spine and the posterior superior iliac spine, here and here, we are able to measure pelvic tilt, which is a concept you may have come across or may have heard, and this is tilting of the pelvis in the sagittal plane. The posterior superior iliac spine is a difficult one at the best of times. if you've ever been on a beach and seen someone with their shirt off and seen their back, you might notice two dimples in the small of their back in the lumbar region. That represents the posterior superior iliac spine on the either side. But these can be tricky to find. Some people it can be almost impossible, particularly if they have more fat mass, or in case of others just structurally different. I know I've known some people where one side's really easy to find, the other side you can't find it at all. One of the best ways is to get them to sit down and just lean forward, and so this flexes the spine and forces this region to the surface and just makes it a bit easier, but can be a tricky one. This is the marker setup that we would have if viewed from above, of course, which would be tricky with the 2D system because obviously the torso would get in the way, but we could have transverse pelvic rotation as well by measuring the motion of these markers. But there we are. There are some anatomical challenges, and something that a colleague of mine sent me. So this I should stay still, really. This knobbly portion here that you can just about see is the humeral tuberosities, the greater tuberosity here, and it's one site that people frequently place markers on, particularly if someone's got a decent amount of deltoid muscle, then perhaps not, because the muscle just gets in the way. But if they're average build, the deltoid, the humeral tuberosity can be a site where people place markers. Now imagine if when their arm is in an adductor position here, you placed a marker there. Well, the position of the bone and the position of your marker aren't going to track as this person performs abduction. You can see the tuberosity moves under shoulder girdle here, whereas your marker would stay put. So there are things like this that we have to consider. No one area is this more true than around the ankle and foot. So there is an enormous amount of movement going on here, and there is a great amount of debate as to how best to measure this motion. So the lower limb, we can have internal external rotation of the tibia, inversion, eversion of the foot. The foot can also abduct and adduct. Interestingly, foot abduction, adduction occurs in the transverse plane, not the frontal plane. And of course we have the flexion extension of the foot. So it all makes this motion very difficult to record, and very often people will use two marker sets on the ankle, which you won't be expected to do, but just to give you an idea of how challenging this can be. Another issue is that ankle flexion extension is not a true sagittal plane motion. So when you lift your foot up, and if you lift your foot up off the ground, you point your toes away in plantar flexion, lift it up in dorsiflexion, you think, okay, sagittal motion, great. Well, for it to be pure sagittal motion, then you would need to have a transverse axis of rotation. It's perfectly horizontal, perpendicular to the sagittal plane of motion. However, the axis of rotation for this flexion extension occurs at an oblique angle to the transverse axis, and you can see this on yourselves. If you look at your ankle, you see these two knobbly protrusions on the medial and lateral side of your ankle. This is the medial and lateral malleoli. One is higher than the other. You can see in the image here. So the inferior portion of the fibula here, this region, roughly, it's somewhat obscured by the line that I've put on here, but roughly here would be where we would place our lateral marker, I should say. Whereas our medial malleolar is higher. It would be here. It's tilted upwards medially. So this creates what we call a triaxial axis of rotation, where it's not truly, it produces a sagittal motion, but in order to do so we have to have something between our normal axes of rotation. So again, it does complicate things. So as I've said, TAM ignore is God knows why it's called TAM. This represents the right femoral, the right. I don't even know what it's called. Oh, because it's right leg, yes, of course. The lateral malleoli marker around here. This is the medial malleoli marker of the right leg here. So we've got right on here R, just to represent the right limb. For some reason, the common convention for the medial malleoli marker is to call it TAM, T-A-M, don't know why. And I've highlighted two here, but the distal portion of the metatarsals, I suppose what you could think of as the knuckles of your feet, if you like. So this would be the big toe, the hallux, and then the second, third, fourth, fifth digit. The distal portion of the metatarsals here, these long bones here in our foot, are where another location we commonly place markers, particularly the fifth, second, and often the first here. These are fairly easy to find if you get someone, they need to take their shoe off usually, or perhaps not if you're doing a shot analysis, which does make things even harder, but just getting them to scrunch their toes up. If you scrunch your toes and palpate around this region, you can feel your distal metatarsals that much easier. You should be able to count all five. And for the sagittal view, we've covered these two here. This is a malleoli marker in the fifth head. But our final one is our calcaneal marker. This large bone here in the ankle is the calcaneus. And our calcaneus marker, which we need if we're going to measure sagittal motion, so flexion extension of the ankle, is positioned based on our palpating of the Achilles tendon. So you basically push down on the tendon, not too aggressively I might add, but once you stop feeling a soft squidgy tendon and start to feel bone, that point where tendon becomes bone, the fibrous enthesis, for those of you that love your anatomy, that is where we place our calcaneal marker. Obviously that becomes trickier, as I say, if someone is shot, but in this case we'll pretend that scenario isn't an option. Okay, so there we are. Hopefully you can now answer our original question, which essentially related to the purpose and the value of motion analysis in sport and exercise biomechanics. As I say, this is designed to complement your practical sessions and will provide you with hopefully a basis to progress in future with your biomechanics lab studies. So there we are. I hope you've enjoyed this, and I'll see you soon.